All right. So previously we discussed simple interest. So in this booklet, it would have been on page 9. Okay, so simple interest, I want you to think of it this way. If you compared time and the interest earned, right? So technically your final amount, right? You're earning interest on what you start off, right? So let's say you invest $1,000 and you invest it at a simple interest rate, your your investment is going to increase at a linear, right, constant growth. You can go back to page 9 and write that down, right? It's linear because you keep earning interest based on that initial amount that you put in. Okay, so that's simple interest for you. Now we're going to talk about compound interest because, um, and I want you to think of an exponential function. So if you were to compare time and the amount of money you have, it would also start, well, you could start at zero and then you wouldn't really earn anything at first. But if you start with any amount along the y-axis, like you put in $1,000, at first it would appear linear like this, it would grow, and then after a while, this would turn exponential. Okay, so compound interest, it's exponential, sorry, exponential growth, synonymous with exponential growth. Okay. So compound interest, um, what it's almost like a snowball effect, right? If you start with a small amount and you keep rolling it, you earn interest on the interest you've already earned. They tack that on, and then you earn interest on the amount you had previously. So it just keeps on getting bigger and bigger fast, right? So at first, it may look linear, like if you were to just compare the first couple of years or first month or so, but then after a while, it will actually grow rapidly, turning into exponential. So if you had to compare compound versus exponential, the difference would be that one is just a straight line, right? So if we start with a linear, a simple interest scenario may at first be better, but then there's a point where linear just keeps going slowly and this goes rapidly up. So we're going to discuss that a little bit more down the road. So back to the point of dealing with compound interest. Um, right? The word compound, you're you're adding to something, right? You're mixing things up and it just keeps compounding. It's a compounding effect, right? So interest is earned on both the principal and the accumulated interest. Not just, it's not always calculating interest on the principal, interest on the principal. No, no, no. It's adding the interest onto what you originally invested, and that new amount, the interest is calculated for the next period. And then it looks at what do you have now? Okay, you have even more than before. Well, we'll pay you interest on that. And so it just keeps on accumulating. Most financial institutions pay or charge compound interest. Compounding periods, it's the amount of times the interest is calculated in a year. Very important. When you see the keyword compound, you cannot use simple interest formula, right? When you see the word compound, you cannot use simple interest formula. So I equals PRT only works when it says explicitly simple interest, okay? Or the word compound is just not there, and you also know it's most likely simple interest. Since you're earning interest on previous interest, it creates a snowball effect. So there it is one more time. This is supposed to be a snowball. Your investment will essentially grow faster, and similarly, your debt will cost you more interest as well. So it's good if you earn it. It's bad when you have to pay it. The relation between time and money, right? Relation between time and money is exponential. In general, we start with an investment, right? The starting amount when you're investing is what we call the principal, and you expect to earn interest. The value of the investment after a period of time is called the future value. I can use letters again. Future values, we use the letter A, and for principal, we use the letter P. When interest is compounded annually or per annum, it means the same thing as per year, right? Per year, let's write that down. That's what this means. And so this is the formula. And so it may look like the one of the simple interest formulas, but no, this is an exponent. Okay, time is the exponent. It's not right next to it. Okay, so you got to understand that. But when compounding periods change, so if it's annual compounding, we use this one. But when the compounding periods change, it affects both the interest rate and the exponent. Okay, when these compounding periods change. So annually or per year, it's just like it's happening once a year, but it could be that the compounding periods change, that it's monthly or daily and so forth, that it will affect the interest rate and the exponent every time you calculate. So this, I would like you to have this version. This is the one I would like you to have when it comes to compound interest. Later on, I'll already give you a secret. This formula can be replaced with an app that we're going to be using, but I need you to understand how this works before we just go into that app called TVM, time value money. Okay, that's on your graphing calculators. A is the future value or the value at maturity. P is the principal. It's the original or initial amount. Rate, compounding periods per year, that's N, so that's how it changes. Notice that if I compare this one to the original, the compounding periods affect the interest rate. You have to divide it by how many times it's being calculated, and look at where N shows up on the exponent, right? N is also affecting the number of times the calculations are being done in a year. So you've got all these things, and that it tells you what each component in this formula represents. I already touched on this, but this is important. If it says compounding periods is N, okay? That's what we're talking about, compounding periods per year. So if it says annually, then it means once a year. If it says monthly compounding, 12 times a year, quarterly, 4 times, bi-weekly compounding, 26. Semi-annually, you got to understand that, that's 2 times per year. Semi-monthly, it's twice a month, which is 24 times in a year, and weekly is 52 a year. I think, let's just add daily. That would be 365 compounding periods, like times interest is calculated. If it's a daily compounding period, then the interest you earn is literally calculated on a daily basis. Okay, so you need to understand that. One more thing on the side here. So to wrap things up, simple versus compound. Okay. This is a constant growth. This is exponential growth. That's how they would be distinct. When you graph them, you would literally get a straight line when you compare the amount you have over time. If you compare this scenario, the exponential, if interest is compounded, your money grows exponentially. Okay? So this is the initial, this is basically 0p, right? Whatever you invest is that point. This is also 0p. It's what you invest, but it's linear. It's steady. It could be, if you were to combine them, time versus amount of money, it could be that you invest $1,000 at 1,000, and it could be that at first, you know, let's say you invest 1,000, compound it, and also in a simple interest situation, it could be, okay, this is simple, this is compound. So I know you will hear me say a lot of times, oh no, compounding is always better. Yes, for sure, in the long run, it's always better. But it could be that there's a short period of time, right? As long as this line is on top, that means you have more money under the simple interest scenario, but then there's a point where you kind of are at the same place, and after this time, you're better off going exponential than simple. So in the long run, compound is better. Okay. So right here, simple is better, and we could actually find the number of months or number of years, right, where these touch. You could have two different equations in there. But then here, compound is better. Okay, so from here on in, compound is better. Within, at the initial deposit and whatever time this would be, simple interest would be better. So I could actually highlight right here, this is better here, but then you would want to, in the long run, go exponential. So if you had to choose and you had to have it a long-term investment, you'd most definitely want compound. Also, if you ever have to choose, when it comes to investing, the greater the compounding period, so the more often your interest is calculated, the better. Okay, the more often, the better. So if I ever ask you if everything else is the same, would you go monthly or would you go semi-monthly? And you would have to say, I would go semi-monthly because it has more compounding periods per year. Okay. All right, that takes us to the 13-minute mark. Let's do some calculating, actually using this formula. So let's keep going. It's actually not bad. It's just plug in and go. Okay, plug in and go. So here we go. Greg is 15 years old and inherited $15,000, $150,000, pardon, from his grandmother, and he would like to invest it so he can use the money to purchase a house when he turns 25. You have to read carefully here. A lot of information is given to you. You just might have to do some subtracting and figuring out, kind of read between the lines. He has the following options. So option 1, 4.5% rate compounded monthly. And option 2 is 4.5% rate compounded semi-annually. So the interest rates are the same, but different compounding periods. How about we say right away n is equal to 12 here because it's monthly, and compounded semi-annually, n is equal to 2. I can tell you that already. So I need you to understand that this is compounded, so we cannot use simple interest formulas here at all. Cannot use them. It will not work. A, calculate the future value. Future value is A. Right, they're asking, hey, what's A for each of these options? Like, how much money do you have under each circumstance? Okay, so here we go. Let's calculate that. We know that the formula is A is equal to principal times 1 plus rate over n to the power of n times t. Okay, and so we will insert what we know. Principal is 150,000. You go 1 plus, what's the interest rate? 4.5%, right? So 4.5% is 0.045. I hope you would know that. Divided by, in this case, the compounding periods for option A is monthly, which we already determined as 12. And all of that is raised to the power of n times t. So it comes up here, 12 times, my time is in years, which is a little tricky here. How much time goes by? Well, Greg is 15 and wants to know how much he has at 25. So I hope you would see that, hey, that 10 years went by. So time is 25 minus 15, which is 10 years. Okay, so this would be times 10. You figured that out. That's the t part of this whole thing. Okay. And now let's calculate that. I'm going to show you this step because it's important. Let's clean this up. So this part we can do. So just grab your calculator. You go 1 plus 0.045 divided by 12. It is going to divide before adding. And I want you to use all decimals. In this case, it's finite. So I'm just going to write the whole thing down. 12 times 10, just multiply that. That's 120. I want you to stop there for a bit. We divided our interest rate, which is a yearly interest rate, by 12. Why? Because we are doing monthly calculations. So you need to take that interest rate and slice it into 12 equal parts, which gives you this here. Then you add that to 1. And I don't know if you see this, but this is an exponential equation where b is bigger than 1. It's going to be a growth, right? Growth increasing function. And my exponent here is 120. So what is it saying? That interest is calculated, this part right here. I will try to fit that in here. Interest is calculated 120 times over 10 years. That's what that exponent tells us, right? So we know everything, so we can actually just figure out what that is. So we go 150,000 bracket. You can copy and paste, close the bracket, right? We know already what that is. And then you go hat. You already know that that's 120. Hit enter. And you get, it's a little dark, what's going on there? There. That's how much money you will have. So at the end, you'll have 235,048.92 cents. So that's how much money you will have. And you can tell that, right, like you went from 150 to 235. Between these two numbers, you can figure out how much interest you've earned, okay, because that's interest you have earned. B asks for calculate the total interest earned for each option. So B, this is what you need to remember. That A, the future value, is always made up of your principal plus any interest that you've earned. Okay, that's always true. So to find the interest, you simply we bring P over to the side basically. So when you subtract how much you end up with, right, you go your future value, like the amount you expect to have in the future minus what you started with, you get the interest earned. interest earned here is 800, sorry, not 800, 85,048 and 92 cents. So in 10 years, by just letting the 150 sit in that account, you've earned $85,000 under this option right here. What's the rate of return? Rate of return is interest earned divided by principal, or initial amount, times 100. And with my interest, I already calculated that, or else I would have done this at the top here. I already have figured out what that is. So it's 85,4892 divided by, you started off with 150,000, multiply that by 100. You get, if you do that, you get 56.70%. That's the rate of return for this investment. We'll do D afterwards. I wouldn't mind you pausing right here and trying option. This is option 1, right? I should say this is option 2. I'd like you to try option 2, see if you can do it without me. So you can pause here and go. So I'll just plug in 150,000 again. 1 plus, the interest rate is the same. Compounding periods it's semi-annual compounding, so that means that n is equal to 2. We go, what does it ask for here? N. So this number comes back up here. It affects the interest and the amount of calculations there will happen in the lifetime. So 2 times 10. So you know that there'll be 20 calculations happening, because when you do something to the power, right, it'll multiply itself, in this case 20 times. So 150,000. You can do however you want, but make sure, okay, you can go 0.045 divided by 2 first if you want, then add 1 to it, like so. So you get 1.0225 to the power of 20. And then, so now we type the rest in. So 150 to the power of, or times this part to the power of 20. And there we go. 234,076.38. And you can tell, not by much, you can tell that you're making less because you have fewer compounding periods. Okay, so this is the answer for A. B, what's the interest? You take this amount, you subtract what you started with, and that gives you 84,076.48. That's how much interest you've earned. You can use that to find the rate of return. How much did you make? Basically, how much did you make over what did you start off with? Compare that to what you started off with. And if you do that, you get 56.05%. So you can tell it's not lower by much, but it is lower. And there it comes back to higher compounding periods, like more compounding periods, better return, better yield. Okay. So D, it says, what can you conclude about compounding periods and the effect on the future value? If all things equal, so if everything else is the same, the amount you invest and the interest rate, a greater compounding period will always result in higher returns. All things equal, right? So that, like, because if you were to change the interest rate, for example, it could be that you would have made more here, even though the compounding periods had been lower. Okay. Take your time, write this down. And I just need to cover one more concept, which is the rule of 72. There we go. Go to page 18. Very powerful estimation tool. It's used a lot in the finance world. So make sure you understand the rule of 72. It has to do with doubling time. Okay, so I'll right away say doubling time. Think of doubling time when you think of rule of 72. It's an estimation tool, right? It's used to estimate how long it would take for an investment to double based on a certain interest rate. It is most accurate when it's annual compounding, but it still can be used with other compounding periods. So if you want to know the time, in years to double your money, notice that the amount of money doesn't matter, but you take 72 and divide it by the interest rate that you're given. Okay, but it's important to not convert that's the only way this works. I usually tell you convert, right? Percentages to decimal, but don't convert here. Leave it. This is essentially the doubling time. Okay. And so the rate required to double an investment. So if you're wondering, this would be, what is the time that I need to double my money? If you want to rather ask, and it's just basically rewriting this, manipulating this equation to come up with this, you basically just swap these two. If you want to know, hey, what interest rate do I need to double my time within a certain time frame, you use this formula right here. I would say not critical to have, as long as you have this one, because right, these are basically the same, they're just rearranged. You just have to make sure you don't multiply your answer by 100 in this case. Like, with this tool, we don't divide our interest rate by 100 to get a decimal, and we also don't multiply it by 100 to get the rate. It is what it is. It's just, don't worry about the times 100 or divided by 100. So example, what does this mean? Mr. D would like to double his $250,000 secret stash in 5 years to retire early. What interest rate would he need? Answer using the rule of 72. Okay. So what you do here, what does it ask me? What interest rate? Right? So it's asking for this. And they want you to answer using the rule of 72. It should ring a bell right away. Okay. Well, the rule of 72 says that the rate will be found by going 72 divided by my time. And we have 5 years here. That's my time. So you just divide that by 5. And you get, if you go 72 divided by 5, you get 14.4 on your calculator. And yes, that is percent. That's it. Okay. So for the money, for the $250,000 to double in 5 years, I need to find, right? He needs to find an investment that offers 14.4% interest, which is quite high, right? So you'd have to go higher risk on that one. B, verify your answer using the compound interest formula. Assume yearly compounding. So this is what they want us to do. Use this one to confirm that this is actually going to be the case. Okay, let's try it. We have 250,000. That's our principal. You go 1 plus interest rate is 14.4. That's 0.144. Here, you definitely want to divide that by 100, right? You definitely want to divide that by 100 when you're using this formula. Divided by annual compounding. So technically, you just put a 1 there. Let's do this one more time. Yearly compounding, n is equal to 1. Okay. It's irrelevant. You don't really need it, but let's just do it so we can see, right? We use that same formula. We just plugged in 1. And then it's 1 times 5 years. So this would be 250,000. And it's basically this divided by 1, which is just 0.144. So it's 0.144 plus 1, which is that. So 1.144 to the power of 5. So technically, when we compute this, we're expecting double this. Okay, double that amount. So let's see if that will hold up. I'm going to copy paste that to the power of 5. Don't forget, close. And remember, this is an estimation tool. Who cares if I'm right at 500,000? This is pretty close. I would be happy with this, right? So it's an estimation tool. Close to double the starting amount, the initial investment. Rule of 72 estimates. And why would you use this? Well, I think it's always nice to see, if, for example, I get a 5% interest rate, I drive around and I see a rate of 5%. So you know your interest rate. You're like, okay, 72 divided by 5, it would take me 14.4 years. You get the same answer as here, I know, but because I just now changed my interest rate to 5, but 72 divided by 5 would take me 14.4 years to double my money with that interest rate. So if you have 100,000, it would take you under that interest rate 14.4%, 14.4 years to double. So let's say you keep driving around and you see an interest rate of 3%. Okay, 72 divided by 3, it would take you 24 years to double your money. So that's how this goes. Let's keep going here. One more page. This is page 19. All right, Heiko would like to invest $6,000 at a rate of 2.35 compounded weekly. Use the rule of 72 to estimate how long it would take for the investment to double. Explain your answer. Okay, so because it says use rule of 72, you have to use it. So what is it asking me? How long? It's asking me for time. So out of the two formulas, you would use this one. T is equal to 72 divided by R, like that. I'll use a capital R knowing that we don't need to divide that by 100. So time, 72 divided by 2.35%. Leave it like that. And so equals 72 divided by, that's 30.64. Okay. I want to explain this. What did you just find? Remember when you found your doubling time with exponential functions? Well, this is what's happening here. At time 0, time and money. That's what you're comparing. At time 0, you have 6,000. Okay. 30.64 years go by. Okay. What's going to happen to your money? It's going to double. Another 30.64 years go by. That gets you to is that 61 something, right? 6128. You double your money again times 2, 24. So basically here, if you do a table like that, you can actually say, hey, it's going to take me 60 years and then some to get my money to 24,000, right? Using the doubling time to help me out here. And I can continue this for a while, right? If I want to know for higher amounts. So this can also be done like that. So, but every 30.4 years, whatever money you had previously is going to be doubled. Okay. Use your answer in A and the compound interest formula to verify. So you can actually type this into your years and verify this. Okay, so let's do that. A is equal to, you start with 6,000. 1 plus the interest rate is 235. It's compounded weekly. Okay? Weekly compounding. That means that n is equal to 52. Very important, you need compounding periods. And then it's 52 times how many years? We use I would use brackets here. This is how many years, so I basically plug that into my formula. I'm going to see here if after 30.64 years, if my $6,000 actually turns into 12 or close to. So let's take our calculators. 0.0235 divided by 52. I add 1 to it. There you go. These numbers get small, especially what follows the 1, once you have higher compounding periods. That is normal. Okay. 52 times 30.64. So this will be 1593.28. So here we go. 6,000 times, copy, paste, close, and then I go hat to the power of, I guess I can just copy paste that in there. And here we go. That's 12,325.09. And yes, you went from 6 to 12,000 in that amount of time, so it works. Verify this using your knowledge of exponential functions. This is chapter 7. I just want you to see that, right? We're going to go y1 is equal to 6,000. And then we're going to enter this amount into our calculator, 1.0004. Let me just get that whole amount. 51923. So some of you are going to like this part, but you let x be unknown. We're going to see if we can get 30.64 here using our exponential equation. Because remember, we start with 6,000, that's A. This is B, which is greater than 1, which is increasing. So let's type this into our calculator and see that. Clear everything. Turning plot 1 off. So it's 6,000. It's 1.000451,923. Close it to the power of x, not just x right beside it. All right. And what's y2 going to be? Well, I want to know, right? I'm going to draw a line which is double of what I started along, right? It's going to cross the y-axis, and I'm going to find the point of intersection there and see if I get 30.64 for my time. So I'm going to go 12,000. Right, you multiply this by 2. Let's graph this. And I know I'm going to be in trouble with my window. So I'm going to go window, X max. I'm expecting something in the 30s, right, for time. So I'm going to go 50. Y max, I start at 6,000 and I go up from there. And in fact, I want to make sure I see 12,000. So I'm going to go 25,000 or something like that. Let's hit graph. Oh. Oh yes, I forgot something. We can't just go X. Good thing this happened to me here. It's 52X. So we don't know what time is, but we do know that this 52 has to be there. Okay, so let's go back to the drawing board and make sure we go 52X. That's where knowledge of an exponential is very important, because my window should have shown me everything. There you go. And there's the 12,000. So let's go find it. Second trace 5, enter, enter, enter. And there is 29.50. So we're going to go second trace 5. And this is 29.50 years. Very close to 30.64. Close to 30.64 years. So what basically happened, right, is I found that intersection there. This is the 12,000 line. And so this time right here is what we found there. So exponential functions still work. Watch out for the 52 there. So I think I'm gonna leave this here. Oh no, wait a minute. I think I need to do one more example with you. And then you will have the rest to just do whatever. So come with me to page 20. Last example, solving for the principal using compound interest formula. So we're going to solve for the principal. That's what's different here. For P, if a question asks you to determine the principal, you'll need to substitute in what is given and then isolate P using algebra. Zach has accumulated 45,000, that's P, over that many years, that's T. And the bank shows that he's earning a rate of, right, that's R of 3.99 compounded daily, so N is 365. There's no number, so you need to translate that. How much did he start with? Oh, and I made a mistake there, right? How much did he start with? So this can't be P. What does this have to be? Zach has accumulated 45,000. That's like how much you have at the end, which is your future amount. So this is A, capital. So I have everything except for P. And remember, this is compound interest, right? Compounded. You cannot use simple interest formula here. So we plug everything in. A is equal to P, 1 plus R divided by N times NT. And so what do we know? We know that this is 45,000. We don't know P. We know that. We know the interest rate. Just make sure you're careful dividing it by 100. And this will be over 365. So this will be a very small number. But as soon as you add 1 to it, you'll be able to see the whole thing. And then this is 365 times 3.5 years, 3.5 years. Doesn't matter if there's a decimal. And now you got to clean it up. Clean it up. Okay, don't rush. So essentially, we want to get all of this to just a number. So it'll be one number as a decimal next to P. And we're just going to divide both sides by that number. So grab your calculator. 1 plus 0.0399 divided by 365. I would hit enter there. And then 365 times 3.5. That's 1277.5. It's okay. And then you just raise that to the power. There we go. And that is P times 1.14 and so forth. This is 45,000. You divide both sides by 1.14. 1.14, so forth. Cancel that out. And we go 45,000 divided by that, which is 39,135.12. Okay, so you figured out needs to invest 39,135.12 to achieve the goal of whatever has been accumulated. Okay, there we go. So pages 22 to 26, some simple interest form mixed in there. Okay, there we go.